So we have to write some equations here. In the first case, it's a little tricky because it doesn't tell you what the products are. So how do you figure out the products? Right. So you recognize that this is a hydrocarbon plus oxygen. So that's a combustion reaction. So getting the type actually helps you figure out what the reaction is going to be. So that means we must have CO2 plus H2O. And then we have to balance it. So that means four here, four there, and that's 12 oxygen, so 6 here. All right. Next, we've got ammonia reacting with hydrochloric acid. So why am I stuck on green here? All right. Well, oh, okay. That's fine. All right, let's try that again. We did that one. So NH3 plus hydrochloric acid, which is HCl, forms ammonium chloride. So ammonium is one of the ions from the list, NH4 plus. So ammonium chloride is going to be NH4Cl. And that is balanced as it is. So that's a combination reaction. Aluminum metal, that's just Al, and iron 3 oxide, Fe2O3, react to form aluminum oxide. Now aluminum we know is also a 3 plus ion, so aluminum oxide is going to have that same formula. And iron metal, that is not balanced, so we need 2 here, 2 there. And what kind is that? Yeah, that's a single replacement. Okay. And then a masses to moles kind of problem. So we have this CaCN2 reacting with water, and the equation's already balanced for you. So we just need to plug in numbers for that. So we'll have 5.24 grams of CaCN2. And I believe that's, well, anyway, it works out fine. So then we want to go from grams to moles. Then moles of this one. 2 moles of NH3, okay, because that's what the question's asking. And then finally, from moles of NH3 to grams of NH3. Okay, so we can calculate that. I don't have my calculator up yet. Hold on. All right, so the mass of CaCN2, that's going to be 40 plus 12 plus 28, 80. The equation tells us that there's 2 of these for one of those. And then NH3, 14 plus 3 is 17. So if we run that full calculation, that is 5.24 divided by 80 times 2 times 17, 2.23. And that's grams of ammonia produced. All right. So keep working on those kinds of questions. You'll see those again, but they're always the same. So once you know how to do one, you know how to do all of them. And then finally, when hydrogen and oxygen gases react, how many moles of oxygen are required to react with 2 moles of hydrogen. So in this case, normally I would not tell you that oxygen and hydrogen are the diatomic gases, O2 and H2. You would need to know that. I figured for the quiz I'd give you a hand with that. So that's H2 gas plus O2 gas. And what does that make? Right, that makes water. That's not balanced, but we saw this kind of a reaction in class. So we've done this a couple times already. Right? And then in this case, you don't even need to really do much of a calculation. The question is asking how many moles of O2 do you need to react with 2 moles of H2? Well, the equation tells you 2 moles of H2 require how many moles of O2? 1. So we need 1 mole of O2. That's it. No. It's good practice to write the equation because often you'll need it to actually answer that question. It just happens to kind of work out this time. But no, the question asks for how many moles, if you got how many moles. Okay, any other questions about that? All right, so move on. We're starting a new chapter today. Speaking of which, I forgot to load it up, so let me do that. Oops. Chapter 8, which is gases. I hope they fix this thing. Gases. Okay. This is the first time we're dealing with gases. We've obviously talked about that gases exist and all of that, but in this case, we really want to know how do we describe gases? How do we account for the kind of unusual behavior of gases that's very different from the behavior of liquids and solids and solutions and things like that? We're not going to do the calculations in this chapter. So if you look through the book, here, you'll find that many of the chapters or many of the sections have these equations and these kinds of these kinds of calculations throughout. And most of the problems also have these kinds of calculations. So ignore that. We're not doing that in this chapter. It's going to be a quick chapter. We're just going to look at some concepts. The only calculations we're doing here are unit conversions, which we've already done, going from one unit to another. So ignore all the stuff about calculating volume from pressure, calculating pressure from temperature, all that stuff. We're not going to do that in this class. We're just going to talk about kind of the general nature of gases and how they work. So when you're in Blackboard, the reading sections and the problem assignments account for that, but there's really not that much to do in this chapter. All right. So how do you measure how much of a gas you have? In other words, what's special about gases that makes them different from liquids and solids? And like anything. You know what a gas is, mostly? So what's different? What makes a gas different from a liquid or a solid?
It's an operate.
Yeah. So like it's a gas, yeah. So what does it do? What's different about it?
You can't like hold it physically.
You can't hold it. Okay. So like if you were able to like seal your hands like that, would there be gas inside your hands or not?
Yeah, but you can't like feel it.
You can't feel it? Okay, yep. What is that? Let's think about it this way. An empty beaker. So this is a 600 milliliter beaker. How much gas is in the beaker right now? 600 milliliters? Okay, yeah, so it's filled with the container. What if we went to a high pressure environment? We pressurize this room. How much gas would be in this container? Yeah, there'd still be 600 milliliters, but there'd be more gas in there, right? Because it would be pressurized. So how do we account for that? I think it's that issue of pressure, that it's hard to measure the amount of a gas. You can't measure it with volume alone because that can actually change based on the conditions. What's a way to measure gas that it wouldn't change? Yeah. Do gases have mass? Can you weigh gases? What do you think? Yes? How would you weigh a gas? Any ideas? You can do it. What's Yeah, if you could keep it in a container under a certain amount of pressure, like a balloon, for instance, that's one way you could do it. You could weigh the balloon empty, then you could fill the balloon with gas, weigh it again, and see if it's changed or not. We're going to do that in lab tomorrow. We'll play with some gas stuff. So that's one way to do it. That can also be a little bit complicated, like a helium balloon. Has anybody, you've seen helium balloons, like the ones that float? So how much do those weigh? Not a lot. Yeah, they actually have a negative weight because they go up, and weight is a force on the ground. So that's a little tougher to measure maybe. So we have to think of some other parameters, and that means when we talk about gases, we're usually talking about pressure as a measurement of how much gas you have, and then also mass. But it's not always clear how we measure mass, so often those things are related. To talk about that, then let's look at pressure specifically. Because that's not something we've really dealt with before. What are some units of pressure? You may know? P. What's that stand for? Close. There's another letter in the middle. Yeah. Has anybody ever measured pressure of something before? Bar, that's one of them. Yeah. What do you say? PSI. Yep, PSI. So we've got, great, glad that's happening again. Okay. Bar. We've got PSI. What does PSI stand for? Anybody know? Yeah. Pounds per square inch. Which, if we wrote that in the way that we normally write our units, is pounds divided by inches squared. And think about what that means. That's a nice unit because it tells you exactly what it is. It's a pound, which is a unit of force, over an area, a square inch. So if you put a 1 pound object, if you shaped it so that its contact with the ground was 1 inch, that would be 1 psi that it exerts on that ground. So pressure isn't just about force, it's about force over a particular area. So there's an area component of that. An example of this, we all have a particular weight, which is our force on the ground. But the pressure that you exert on the ground can change depending on the size of the area that you impact the ground with. Has anybody ever worn like shoes with really small heels, small ground contact? Like not big, you kind of have some. Yeah, so you have a little bit less area on the ground. So if you have them, especially if they're really small, and you go walking in like a field or something, what happens? Yeah, you sink into the ground. And that doesn't happen if you wear flatter shoes, even though you weigh the same. You might feel heavier on the days that you're sinking into the ground, but it has nothing to do with a change in your weight. It's just the size of your shoe, the size of your force over the ground. So that's the pressure that you're exerting over the ground. These are actually some units that we're not going to used too much in this class. They're used in the world. Bar for kind of a, well, we'll get into what all these things mean, but PSI we use in things like tire pressure. Right, everybody check your tire pressure recently. Should you probably do that? Change in temperature and all that. You don't want to be driving around on low tires. But the ones that we're really going to focus on in this class are the ATM, which stands for atmosphere. One ATM is the pressure exerted by Earth's atmosphere at sea level. So if you are at sea level, there is a bunch of air pushing on you. That's the atmosphere. And the amount of pressure that that is exerting is called an atmosphere of pressure. That's where that unit comes from. So we'll often talk about pressures, even like in devices and stuff like that, as atmospheres, just because it's a convenient unit, we have a good sense of it. We know that 1 atmosphere is like normal pressure, what we're feeling right now, roughly, because we're pretty close to sea level here. The other type of unit that we're going to look at, oh, I guess that's why this thing isn't working. Like end of it just came off. See if it still works. Oh, yeah. The other unit we're going to look at is millimeters of mercury. That seems like a weird pressure unit because it's millimeters. Millimeters is a length. So what does that have to do with pressure? Well, we can convert it. There are 760 millimeters of mercury in 1 atmosphere. And the reason this is a pressure unit has to do with a device, actually, that we're going to look at. Hopefully they have a picture here so I don't have to draw it. Yeah, here it is. We'll put that in there. What you can do is you can take don't actually do this because it's super poisonous and dangerous, but you could take a container and fill it with mercury. Mercury is poisonous, as you probably know, right? But the dangerous thing about mercury is that it's also volatile. So when you have a sample of mercury, it's actually making mercury gas also. So you can inhale it pretty easily. That's why you don't do this. So take a container, fill it with mercury, and then you evacuate a tube. You take all the air out of a tube, and you invert the tube into the mercury. Mercury is going to push up into that evacuated tube, right? And why is that? Well, because the atmosphere is pushing down on the rest of the mercury, forcing it up the tube. The distance that the mercury will travel is 760 millimeters. So that's how much force the atmosphere can exert. It can exert enough force to push that up 760 millimeters, which is about, I don't know, that high or so, 3/4 of a meter. And that's where that unit comes from. So 1 millimeter of mercury is how much that mercury can get pushed up there. You do need to know this number, 760 millimeters of mercury. So make sure you know that that is atmospheric pressure. And these are the 2 units that we're going to use mostly. There are some other ones. There's Pascal is one that's sometimes used in the metric system, another pressure unit. But we'll focus mostly on atmospheres and millimeters of mercury. So let's look at relationships. This thing's gonna freak out a little bit now and then because the end fell off of it. So we're talking about now all those different properties that I mentioned earlier. I said, well, if pressure changes, then volume can change. If volume changes, pressure can change. There's temperature issues as well, and then there's amount of gas. And all these things affect each other. And since we're not going to be going through the calculations in this class, what we do want to know is how does this thing affect this thing? So if we change this one, what happens to this one? And that's what we're going to focus our time on this week. So first, we'll look at pressure and volume. And just because of our scheduling, this will make a little more sense tomorrow because we're going to see all of these things in lab. But what do you think happens if you have a container that you then change the size of without changing the amount of gas inside? So that's what this is really saying. Changing volume means changing the size of the container. What do you think happens to the pressure? So for example, you have a balloon, all right, filled with a gas. If you decrease the volume of that balloon without letting any air out, what happens to the pressure of the gas inside? Does it go up or down? Yeah, it increases, right? It goes up. Because in order to make that balloon smaller, you have to pressurize the contents of it. So a lot of this stuff is kind of, we have a sense of it already in our brains just from our experience in life. But yeah, that's exactly right. So we would say that an increase in volume or a decrease in volume leads to an increase in pressure, assuming everything else is held constant. The example that we're going to see tomorrow, we're going to take a bell jar, which is just a domed plastic thing that we put over a surface. And we've got two balloons that we're going to put in there that are just barely filled up with air, just a little bit of air in them. All right, so we've got like a red one, blue one, these little balloons in there. And we're going to attach a vacuum to that container. So we'll have a hose on it. And we're going to suck the air out of the container. So what happens to the balloons if you suck the air out of the container? Close, but the opposite. Yeah, the balloons will get bigger. So you take the air out of the container. There's still the same amount of air inside the balloons, but you've reduced the pressure. So the volume of the balloon has to expand with the decreased pressure. So it's the opposite of what we just wrote there. Decrease in volume is increase in pressure. In this example, a decrease in pressure leads to an increase in volume. So when we do that vacuum, what we find is that, or what we see, is that after doing that, the balloons get quite a bit bigger. Squish against each other here. So you decrease the pressure in the container, there's not as much air around there, then the same amount of volume in the balloons takes up more space. So that relationship between pressure and volume is known as Boyles law. Another way we might word that is to say pressure and volume are inversely related. That term inversely related means when something happens to one thing, the opposite happens to the other thing. When inverse relationship means one goes up, the other one goes down. And so that's what I want you to think about with pressure and volume, is just to understand that relationship and to think about that relationship. Now, the best way I think to keep all these straight, because we're going to go through quite a few of them, is to have an example in mind. Whether it's this example that we do tomorrow in lab, or some other example that you can think of that you know about, where there's a difference between pressure and volume, that will help kind of keep it in your brain. Another one that people think about is a syringe, like this little syringe thing. If you, without the needle on it, if you stick your thumb on the end of it and you push the plunger down, you're decreasing the volume of the space in the syringe, and you're increasing the pressure by pushing on it. So that's another example of this particular effect. All right, so the second relationship we're going to look at is the relationship between volume and temperature. Because actually, temperature is an important factor in properties of gases as well. What happens if you heat up a sample of gas? What? It makes whatever you're heating up bigger, right? Has anybody ever seen this? Seen an example of this happening? No. Okay. Yeah, I didn't know if anybody had any good examples. The example we're going to use is the opposite. What? Like in the sky, like a hot air balloon? Yeah, that's part of it. Right, that you heat up the air and then it expands, and so there's less air in there to fill the balloon, and then it goes up. Yeah, that works. We're going to do it the opposite. We're going to cool down a balloon substantially with liquid nitrogen, so make it super, super cold, and you'll see an entirely full balloon completely collapse into almost nothing. And then as it warms up again, it'll go back to its normal size. So this is an example of a direct relationship, which is the opposite of inverse relationship. One goes up, the other goes up, and vice versa. So when you're heating up some gas, you increase the volume of that gas. That's one reason it says there's all these warnings if you have pressurized cans, like aerosol cans, that kind of stuff. There's always warnings on them not to let them get too hot, not to leave them in a hot car or throw them in a fire. Because what will happen is the gas inside gets heated up, starts to expand, and in this case, those cans can't take that pressure increase, and so they end up exploding. So we'll see that. I guess we'll draw another picture since we're going to see it tomorrow, where we have a pretty big full balloon, and we pour liquid nitrogen on it, which is super cold. and it makes the balloon kind of completely flatten out. But then when it warms back up again, it comes back. So it's not that any gas actually left the balloon, it just got cold and so takes up less space. All right, so that law is called Charles' law, showing that relationship between volume and temperature. So you can take a look at that. Sure. The next one we're going to look at, which we'll also do tomorrow in lab, is pressure and temperature. So what do you think the relationship is between pressure and temperature? This is actually the aerosol is a better example for this one. If you increase the temperature, you're going to increase the pressure. Another example of this is with car tires. If you ever, well, first of all, where can you usually find the information for how much air should be in your tires? You know? Sometimes it's in the manual, but it's also usually posted on the car somewhere. It's usually in one of the doors. If you open the driver or passenger door, there's a little sticker, and it usually says on there, cold pressure in PSI. So what does that mean, cold pressure? Like you can only check it in the winter? It just means that as the wheels heat up from driving, because of the friction, that's going to warm it up. And because there's a relationship between pressure and temperature, as that air inside those tires warms up, it's going to pressurize the tire more. So I don't know if you've ever seen this, but some modern cars have the pressure monitoring little thing where a light comes on your dashboard if the tire gets too low in pressure. And sometimes like on a really cold winter morning, that might be on, and then you drive for a little while and then it goes off. And that's because the pressure has increased. Now, that's not safe. That still means that your tire needs more air in it because you want to check it when it's cold before it's warmed up. And that's what the pressure should be. It also means that if you've been driving for a while, you pull in the stops to a gas station or something and you check your tire pressure, it should be a little higher than what's listed on the sticker or on the manual because you've been driving, so it's warmer than what's listed by a couple PSI usually. So, all right, so that's pressure and temperature. We have this neat device to do this, but measuring pressure and temperature is a little bit tricky because you need something that resists the pressure. So the tire actually is only an okay example because tires change volume also. They get bigger and smaller a little bit. So that's not necessarily a great example. What we have this device that has a metal sphere on the bottom, a stainless steel sphere. And that is, steel, obviously, it can resist a lot of pressure, and it's filled with just 1 atmosphere of gas. And there's a gauge on it with a little needle that tells you how much pressure is in there. And what we're going to do is submerge that in something cold, like ice water or dry ice. And when that thing gets submerged in the cold, we'll see the pressure on the dial go down. So we'll see that the pressure of the gas inside there has gone down. That shows that you can't do this kind of thing with balloons because balloons change volume. So you need something with a fixed volume that's not going to change as you change the pressure or as you change the temperature. So this is also a direct relationship. A decrease in temperature leads to a decrease in pressure. Before we jump on to the next one, we should also note This first one, Boyles' law, the relationship between pressure and volume, also explains how our breathing works. Does everybody know how breathing works? You breathe in air. That's, yeah, is that the technical?
No, there's
Oh.
your lungs want to like equalize. So like
Yeah.
as you let air out, air comes in.
Right, yeah, you got the right idea. So what you're doing is your diaphragm, which is a muscle below your lungs, changes the volume of your chest cavity. When you breathe in, what you're really doing is increasing the volume of your chest cavity. And if you increase the volume of something, the pressure goes down. So when you make your chest bigger by not that much obviously, but by expanding your diaphragm, then the inside of your lungs is at a lower pressure than the outside air, than atmospheric pressure. So air rushes in to fill that difference in pressure to equalize it, as you said. And then when you breathe out, what you're doing is increasing the pressure in your chest cavity by making your chest cavity smaller. So you're decreasing the volume, which pushes the air out. Because again, it wants to equalize the pressure. So that is another example of this happening, this relationship between volume and pressure. All right, the last relationship we're going to talk about, oh, you don't need to know all these names, but this one is called Gay-Lussac's law. And then finally, this one goes by fresh. Moles of gas and volume. This one is pretty obvious, I think. An increase in moles of gas leads to an increase in volume. So that seems obvious. You put more gas in a balloon, it gets bigger. But there's something a little bit tricky going on here because we're only counting by moles of gas, not the mass of gas, which means it has to do with how many particles of gas there are, not how much gas in a mass sense. And take a look at this example. So let's say you fill a balloon with oxygen. And then you do this reaction. This is a reaction that can happen with UV light and some other stuff. The oxygen in the balloon is converted to ozone. Oxygen is O2, ozone is O3. So we convert all the gas in a balloon from oxygen to ozone. What happens to the balloon? Well, is this equation balanced? It's not. So let's balance it. We're going to need 3 of these and 2 of these. So you'd think if you put a certain amount of oxygen in the balloon, you seal it off, and then all you do is turn the oxygen in that balloon into ozone, nothing really happens. But this law tells us actually something is going to happen. What's happening? What changes in the moles of gas in this reaction? What? Yeah, it goes down. So if we started with 3 moles of oxygen and we did this reaction, we'd only end with 2 moles. If we started with 1 mole, we only end up with 2/3 of a mole. So we're decreasing the number of moles of gas, which means that the volume will decrease. We haven't taken any of the oxygen out. We haven't increased the pressure or decreased the pressure. We haven't changed the temperature. We've only changed the volume, or we've only changed the number of moles, and the volume decreases. So that's kind of what happens here, and this is known as Avogadro's law. We have to think about maybe why this is happening. So this happens because of some properties of gases that we're going to get into called the kinetic molecular theory. But one thing I want to focus on before we do that, you'll notice each of these has the name law in there: Boyles' law, Charles' law, Gay-Lussac's law, and Avogadro's law. We talked about this at the beginning of class, but what is a law when we talk about in terms of science? Is a rule. Yeah, it's a set of observations, so something that happens over and over again. And notice something missing from these, why these are called laws and not theories. There's something missing here, and that is an explanation. Nothing that I've just told you explains why any of this is happening. I've just said this thing happens, and this thing happens, and this thing happens, and this thing happens. If pressure goes down, volume goes up. If pressure goes down, temperature goes down. Those are all just things that happen. They're not a reason for something happening. So the next step is to go back and think about why. What is actually causing these things to happen? What is it about the behavior of gases that makes a balloon filled with oxygen suddenly shrink just because the atoms arrange themselves in a different way? What is it about the properties of gases that makes the pressure go down when the volume goes down, or goes up? So these kinds of questions of why is this happening, to me, that's really the interesting part of this chapter, of this topic. How can we explain what's happening? So we're going to do that on Thursday, since we don't quite have time to get into it right now. But we will pick this up tomorrow with the demos in lab. Now, there is an actual lab tomorrow also. It's a chemical quantities lab, so we'll practice mole calculations and all of that. But we're going to do the gas stuff also as a demonstration. So I will see you tomorrow. Thanks.